where it was tails. So this is just a basis of the entire lab.
So what is going into this W bar? What does he do?
So here you mean?
Yeah, what's the measurement performed on?
So yeah, so the measurement, so this whole system here, I call L bar. So this is the entire lab without the spin. So the spin is of course, before time 10, F bar has created the spin and sent this spin out away. So the spin is no longer here. But L bar is now everything that remains. It's the whole lab of F bar and all the devices in the lab and everything like that. And these are now depending on whether, let's say, if I initialized the quantum random number generator with an H bar instead of this state here, then the lab would be in a particular state which I call H bar as well. And if the random number generator was initialized with tails, then it would have been. Then I would call the state tails, and now I can make superpositions of these states. Of course, it's a much bigger system, so actually to say it's only this basis, I could say we're only interested in that state, okay, and everything orthogonal, all degrees of freedom orthogonal to that we call failed. It doesn't need to be one vector. Does this clarify your question?
The state is not pure, right? Because it's missing the spin.
This one is pure.
No, yes.
Sorry. Yes, right. Yes, the state of L bar will not be a pure state because indeed the spin was sent out, so there is actually, this lab will, as a global state, be entangled with that. And actually we can write down this state, if you like. So what is the state, let's say at this point? So let me draw here a line and ask what is the state of the entire system here? And maybe I should do that because that helps what we want to do next. So I could write down this state. What is that state about? So this is a state which involves the lab L bar and the spin. I mean, I don't yet want to talk about L because S hasn't been measured. So what's that thing? I can just write it down because with amplitude 1/3, the outcome of the random number generator was heads, and therefore the lab will be in the state head. And the spin, by the rule that is written here, will actually be prepared in the spin down state. That's just what the rule says. But then I have another component, which is 2/3. And with this amplitude, the outcome of the random number generator was tails. And the spin, by definition, was prepared as spin right. So that's the state of that we have. I hope this further clarifies what I meant by these things. Actually, we can just use that now because I can expand this and say that, let me just copy it here. So this is heads and spin down. But here on the right-hand side, I know that spin right is spin up plus down. So I can write this as spin down. So the first thing is always the lab, and the second is the spin, and spin up. So there's a component with spin up. So I hope this is also clear. I just expanded this here. This is another way of writing that state. And one thing that will be important for the next step is to notice that this state here is orthogonal to the state OK on the lab bar and down. Okay, that's maybe the only technical consideration this whole salt experiment that one needs to make. One needs to verify that this is indeed orthogonal to that. Why is it orthogonal? So by definition, so this part here is actually the state fail, because fail, well, you see, I always define the OK with a minus sign, but here's a plus sign in between. So this is actually fail, spin down. And so clearly this thing, this vector here is orthogonal to that because OK is by definition orthogonal to fail. But it's also orthogonal to that part because here we have a spin up and here we have a spin down. So this big state we have is orthogonal to that. And that I will use now because now I can write another statement. Actually, I will no longer need this. We just rewrote this. So I can erase this thing and say this was the state, psi L bar S. And now I can make a statement that W could make. And now is the last test, whether everyone is still attentive. So let's say he got the outcome okay at, let's say W bar finished the measurement at time 29, before this 30 measurement. Then he can be certain about the following. Then I'm certain, so that's what W bar says, that F knew something about Z at time 0.90. So what does he know about Z? So now we have to use that this is orthogonal. So he got okay, and does anyone see that? No? Okay. Any guesses or any? Okay. Up, yes. So why? So we just said this state here, which is the relevant state to answer this question, because we somehow want to know how we want to relate the measurement here with the measurement done here. So this state is orthogonal to that. So this means that if the outcome is actually okay, then the other component has to be up, which means the measurement that F does is up. I mean, this is a calculation everyone could probably easily verify. This is just basic quantum mechanics. It's maybe a bit confusing if I write it here, but I think no one ever disputed that. So this is just a conclusion that we would make if I was W bar, I would say if I now see that outcome, I know what Z was. Okay, now we have essentially all we need to come to the contradiction that I announced. So we have now 3 statements by 3 different agents, and now I somehow want to combine them. I mean, at the end we will need one further easy thing, but let me now first do this combination. Okay, so these statements are all statements that are, I think, undisputedly valid if quantum mechanics was applicable to systems of that size. Of course, that's a big assumption, but if we make this assumption, then these are clearly statements that these people would make. I mean, this is just what the theory tells them to do. This is unambiguous in that sense. They just chose this relatively careful formulation about making these statements always personal to the agents, so to speak. But now we can combine them. And first I just do a logical combination. Let's now write down a new statement S prime that F could make. So F could make the following statement. If Z is plus 1/2 at time 19, then, and now this looks a bit complicated, but he or she would now say, then I'm certain that this thing holds. But if this thing holds, then she's in particular also certain that about what statement F bar would make. So then, and now I'm not collapsing, so now I'm just logically combining them. So then I'm certain that F bar is certain that W will know W equal fail. I will here not write the time. So this is always at time at the very end of the experiment. So this is a statement that I can certainly make. This is just combining the two. This is just talking about what someone else knows. Now there is a statement which is much more problematic, but I will nevertheless make it. But I will explicitly say that this is an assumption. I will now make the following assumption. I will make the assumption that if, let's say, I use quantum theory, and let's say I know Matthias very well, I know he's very reliable. If he uses quantum theory, it's also, I can trust that. I mean, this is not really about trust, but I just assume Matthias uses quantum theory correctly, which is certainly a correct assumption. Now, let's suppose I can make the statement, I know that Matthias, when he did this calculation, came to the conclusion that this particular value must be plus 1/2. Then I could say, because he used the correct theory, this means I now also know that the value is plus 1/2. So that's a conclusion that I'm now going to make. So more concretely, I'm saying that if this statement here holds, then we should be able to conclude that if, or SF, this is another statement of SF, let's call it bar prime prime. This is now not a logical conclusion. This is a conclusion under the assumption that we can in that way be consistent. So if I know that someone knows something, then I can also know that if I know also that this person used the same theory. So or I could also say if I know that if I took the perspective myself of Matthias, I would have arrived at that, so therefore I arrive at the same conclusion. So I now kind of collapse this into this statement that will know W equal fail. So I now use this assumption. And I want to stress again, this is an assumption. I mean, up to this point, there was only a logical combination, whereas here is an assumption that we can in that way combine knowledge. Okay, now I need one more step, and I think now I use this feature of this. Okay, now this is, there's only, okay, now it doesn't work in that way, yes.
No, it can work, I think it goes up.
Yes, but only the middle part. Or is
the middle part? Oh.
Anyway. Actually, maybe if I was very clever, I could move it up a bit, and it would just give the new statements I wanted to write. Anyway, let's. I mean, I think it's. So I will no longer need that first statement, so I can just erase it. So let me do that. I will also no longer need the second one. So we can erase these two. And I will only need these two lines. So then we are essentially almost done. So I will now, here I took F's perspective. Now let's take W bar's perspective. And again, I can make a statement which is essentially almost the one that is already here, which is the statement that if W bar is equal to OK at the time 29, then, so he says he's now certain, and he can now use that thing here, that F is certain that W will know W equal fail. And now again we do this step, this assumption that I called C, which allows us to contract this statement into the statement that if, he says, if I've seen OK at 0.9, then I'm certain that W will know W equal to fail. Now I did the same step as before. He knows that someone else is certain, so he's therefore also certain. Now let's suppose, and this is of course a trivial addition, that W bar announces the result to W. Now W can make a statement, which is the following. So actually maybe I need still one more line here. So W can now make the following statement. So this is the kind of final statement, almost, in the following sense, because W could now say, if W bar announced W is equal to OK, then I am certain that W bar is certain that I will know W equal fail. And now, one last time, if you want to really be precise, I could again use this C and contract this, then it's a bit more striking, to the statement, if W bar announced W equal to OK. I forgot the time here, but that happens, this announcement happens at time point 29. Then I'm certain that W, which he will observe himself, is equal to fail. And let me now add the time, this is at 39. So he has now arrived at this final statement here, so that let me put that into, or mark it with a color. That's kind of the final statement, W arrives. And now remember what we needed to arrive at this statement. We needed that all these statements were derived within quantum theory, universally valid quantum theory, and we use this assumption which I call C, which means that if I know that someone knows something for certain, then I'm also certain under the condition that the person used the same theory that I would have used. Okay.
It is announcing details, it's not
Pardon?
a problem. Somehow you have to be very precise about.
Yes. So, yes, this announce. No, okay, yes, no, this is not, I mean, because it would be a problem if one of these friends would announce something because they are in isolated labs. But of course, W bar, I mean, you could just say he now sends, I mean, clearly W bar can now send the outcome to W. I didn't draw it here, but I could even, I mean, like in the same way as the spin is transferred from F bar to bar, I could say, let's suppose that he now sends that to this guy. So he knows that. I don't think this is, okay, I mean, this is kind of at the outside, so W is not in the box. But you're right, I mean, if I did